So let's take a look at some specifics here, or at least, I guess we'll start out with some vocabulary. So Q stands for heat, of course. I assume Q originally stood for quantity, or whatever the Latin equivalent of quantity is, but this is energy transferred between objects because of temperature difference. So it is possible to have delta Q, but generally Q already is talking about a change in energy. You're transferring energy in, and so you typically do not see a delta in front of Q. I have some sort of cube right here of material, and based on my notes, I think I'll probably be using this in just a moment. I have 50 grams of aluminum. There's some sort of energy I put into it, and that is going to cause a change in temperature. In other words, we're getting the particles to move around a little bit faster inside. So sort of a microscopic change in kinetic energy causes a change in temperature. So there should be some relationship between the amount of energy I put in and the change in temperature. The more energy I put in, the greater the change. If I take energy out, I should have a loss of temperature. It should cool down. You could also look at that if I take a hot cube of aluminum and stick it in the room, energy is going to radiate into the room because there's particles that will hit the cube, and because the particles in the cube are moving faster, the particle is going to hit it and bounce back a little bit faster, so the temperature of the room will increase and the temperature of the cube will decrease. So we're transferring energy from cube into the room. So let's talk a little bit about temperature, and then we'll talk about the relationship between Q and delta T. So let's just start out with the SI unit of temperature. What is the international standard? That is a unit that's not the international standard, but and technically it's degrees Celsius.
Kelvin?
There we go. Named after?
Kelvin.
Yeah, Lord Kelvin.
It's not degrees Kelvin, right?
Correct, it's just plain old Kelvin. At this point, I might have transitioned completely over into Celsius. You might occasionally hear me say centigrade instead of Celsius, just because that's what I was taught. And the centigrade, I think, is officially not supposed to be used anymore. But called centigrade because you basically go from freezing to boiling point, and it's broken up into 100 grades, or centi, meaning 100 grades. But this is degrees Celsius, named after. Yes, and then our unit of system, or unit of measure.
Fahrenheit. Degrees Fahrenheit.
So degrees Celsius, degrees Fahrenheit are the ones that you most run into in the everyday world. Kelvin is what you get more of in science. So these are sort of analogs of each other. This is the everyday world. Kelvin is metric, so these two are very much related to each other. But what is the sort of degree Fahrenheit equivalent or analog of Kelvin? Actually, before we do that, let me give a little bit of background here. So degrees Celsius is based upon 0 degrees Celsius is freezing of water, 100 degrees Celsius, boiling point of water. Fahrenheit system was set up where 32 degrees Fahrenheit is freezing of water, and 212 degrees Fahrenheit is boiling. So the question is, this makes sense. Water is sort of universal. So you can set up a scale here that everyone should be able to get 0 and 100. We established a scale that's pretty much worldwide. But 32 and 212? What's going on there? How on earth did he come up with that? The coldest thing that he could make, he established as 0. So there was some sort of, I think it was a salt-water combination, which he left outside. So the coldest thing that he could create, he established as 0. And then the other number that he established was, I think it was body temperature, which he set at 96. Obviously, he was either a little chilled that day, or the scale has changed slightly over the years. But 96, what's so special about 96? Think back to Babylonians and the number 60. What was special about 60? And more than that, yeah. It's the fact that 96, a lot of things go into 96, and so that was one of the reasons for picking 96. It in theory, made the math easier. And and then over time, things have shifted slightly. What's average human body temperature right now?
It's like 98, yeah.
Pardon?
98.
So where does 98.6 come from? I think officially it's 97.9, but 98.6, it's that classic body temperature. Where does that come from when that's actually not the average?
Does that depend on where you live?
Almost. Not where. When.
I was gonna say when, but it makes sense.
98.6 came out. I kept wondering this because, you know, you go into a doctor's office nowadays and they say, if you had a fever, and I'm going, all right, what's a fever? And to them, it's above what, 101? Or above 100? I
My
forget.
life rate is like 199 or 100.
Okay. So I kept wondering what's 98.6 because I flashed back to elementary school. I was feeling sick and I went into the nurse's office. She took my temperature, it was 98.4. She said, well, you don't have a fever because it wasn't 98.6. And my body temperature typically is below 98. So.
That was a fever for you.
Yeah. But 98.6, they did a sampling of people in Europe in the mid 1800s, and the average body temperature was 98.6. That's where that comes from. So I've read. And there's some explanations, I can't remember what they are, but there are some explanations for why the average body temperature of humans now is less than it was 150 years ago. So anyway, all right, so we have a scale here set up for Celsius and for Fahrenheit. Kelvin. So if I have a gas and I start to slow the particles down, in other words, if speed goes down, kinetic energy goes down. And they thought, well, what happens if all the particles stop moving? Then what's the total kinetic energy?
Zero.
Yes. So they said, well, you can't get lower than that. And since kinetic energy and temperature are definitely connected to each other, they established 0 Kelvin is when everything stops. This is what they call absolute zero. It is the equivalent of negative 273.15 degrees Celsius. Matter of fact, the conversion between Kelvin and degrees Celsius is just a matter of adding or subtracting 273.15. However, you have large chunks of people who are using degrees Fahrenheit, so there's got to be an absolute zero in this scale. So keeping vague memories of this person alive, or this unit alive, anyone happen to know what absolute zero is, or the scale where 0 of it is absolute zero, given our unit system? I feel bad for the guy. Yeah, we're going to name a unit after you, but no one's ever going to use it. Rankine, capital R. So 0 Rankine is absolute, the same as 0 Kelvin.